let us start this lecture from Chanakya, one of the greatest person or educationist, I call him, in ancient India, and he has written a book known as Arthashastra, which you must be aware. And he says that education is the best friend. An educated person is respected everywhere. Education beats the beauty and youth, which was a magnanimous statement what he has given. But if I look at modern education, is not really subscribed to that. Therefore, there is a need to look at modern education and see that how it can help us in pursuing our life towards excellence. So let us look at what we did in the last lecture. We are basically looking at how to carry out a cycle analysis and various notations we have used, and we have defined certain terms like temperature ratio, pressure ratio, right, for the various components. And what we will be doing today, we will be basically looking at now various assumptions of ideal cycle analysis, because to simplify, whatever I will tell you now is basically to simplify the analysis, which all of you know because you have already done the course on thermodynamics and propulsion in your earlier time. So in the particular BTech, the working fluid has the same composition throughout engine. When I say same composition, generally we take is air. If you look at whatever the assumption I will be talking about in thermodynamics known as air standard assumptions. That means, we know that combustors in which you will be adding fuel, it will be converted into various components, various species, but however you are not considering, right? Just for the simplicity's sake. And working fluid behaves as a calorifically perfect gas. The perfect gas, of course it will be valid all the time, because although the pressure will be high but temperature is being higher, you can do that. But here you are saying calorifically perfect gas because the properties won't be changing, although the temperature will be changing as you go from various components of a gas turbine engine or a ramjet engine. Of course, the ramjet engine we will be discussing today. So, that we are assuming for the simplicity. And fuel flow rate is negligibly small in comparison to air flow rate, because if you look at the ratio air to fuel flow rate is around 30 kind of things. Of course, it can vary from 20 to 40 or even more, right? But we are neglecting. Whenever we are comparing, we will neglect. But in other places, we won't be neglecting. For example, if I am talking about TSFC, thrust specific fuel consumption, or thermal efficiency, can I neglect, say that okay, m dot F will be 0? I cannot manage to do that, right? So that way you should understand. Comparison, whenever we are comparing, we'll have to neglect. And isentropic compression in air intake, fan and compression. So compression process occurs in all these three components. So we are saying isentropic, but in real situation it won't be. Isentropic means reversible and adiabatic. How can that possible? It is not possible. Of course, one can say that the fluid is flowing through the compressor and air intake very fast. Maybe heat loss to the ambient will be very low. You can neglect it, but it cannot be reversible. Friction will be there. Without that, you cannot really do much, right? Particularly in compression. So therefore, you cannot have, but we are doing for simplicity. And isentropic expansion in turbine and nozzle, right? And constant pressure combustion we are assuming, right? Because this is the deflagration, and unlike it is not a combustion chamber or the closed volume where combustion taking place, so here the pressure is remaining constant. One example I always give, as if the combustion is occurring in a balloon. But if it is a closed surface, can I say pressure is remaining constant during combustion? It will be increasing, like in your IC engine, internal combustion engine is modeled as a constant volume process. We have seen that adiabatic temperature under constant volume and constant pressure will be different, right? So similarly, this is again we are making and it is not that bad, but however we are also assuming in this the total pressure loss during the combustion is negligibly small. right? Which is not the case. No pressure losses in air intake and combustor nozzle, right? As I told just now, not only combustor but air intake and nozzle, there is no pressure losses. It's not possible in real situation, but we are assuming that. But engine exhaust is expanded fully in the nozzle, right? That means it is a the thrust is contributed due to the momentum, and it is, of course, that is ideal situation, because particularly in rocket engine, other thing which we are not considering, but there you cannot have. Here you maybe some regime it will be expanded fully, in other regime it won't. So with this assumption, now we will be moving into ramjet engine. Keep in mind these assumptions will be valid for ramjet, and then turbo fan engine, turbojet engine, turboprop engine, what we will be discussing under ideal cycle. And what we are doing, we are basically looking at parametric cycle analysis. That means we will be varying those parameters and see how it is affecting the various performance parameters. That is the objective of this cycle analysis, unlike your other analysis what you have done. That it can be used as a design tool. So let us look at ramjet engine. If you look at a ramjet engine, I have shown a schematic diagram. This is having portion is air intake. In this case, the air will be entering and from the supersonic speed, because ramjet engine operates under the supersonic speed kind of thing, and it will be entering and then decelerated. That means compression of air will be taking place, and then it will be burned in the combustors. Of course, flame holder will be there, and once this high temperature, high pressure gas being produced, it will be expanded in a nozzle which is nothing but a CD nozzle, conversion diversion nozzle, right? Let us look at actual cut away view of a ramjet engine. Why the name ramjet is there? Because in this case the ram pressure is being utilized. For example, when the air is coming at a supersonic speed, and it will be having a supersonic spike, and it will act as a diffuser, and the this is known as supersonic compression, right? Till that means the air will be decelerated from supersonic speed to the sonic in the in the intake, supersonic intake, and then from sonic to the subsonic, it will be taking place. Besides this, you need to have fuel, because fuel has to be burned, right? And if for that you need a pump, and then inlet will be there. It is injectors or the atomizers, there will be fuel manifold. Here fuel will be being stored generally, like in your Boeing aircraft, other thing, where fuel is being stored. It is stored in the wing, right? Kind of thing. So therefore, in the fuel injections, that atomizers, it will be there, and then it will be mixed with incoming air, and it should be good. And then when you burn, the flame has to be stabilized with the help of flame holders. Very simple stabilization mechanism is being used, and when this hot gas is being produced at a high pressure, it is expanded in nozzle. If you look at this, is the conversion diversion, which is very, very small, in this case being shown. But then what about this thing? Because there the mixing and combustion will be taking place, it will be uniform, so that and combustion will be complete, because it is at a little higher speed. And keep in mind that here the subsonic combustion occurs, not supersonic combustion. Okay. So now if you look at it, is quite a simpler system as compared to the gas turbine engine, right? Why? Because it is not having compression. If compression is not there, that means it will be not having any turbine. So, and there is no shaft as such, and then the complexity is it is a very, very simple thing. Let us look at a schematic of a ramjet which we will be using, and keep in mind that 0 we are saying is the station number, and 0 to 1 is your supersonic compression, and basically it is the air has to decelerate from supersonic speed to the sonic condition, and Then from 1 to 2 is a subsonic compression. Generally, people design for to achieve 0.3 Mach number of 0.3 at the station 2, at the end of the or exit of the air intake, right? And the total 0 to 2 is nothing but your air intake, like combined with the combination of both supersonic and subsonic. And then of course there is no compression, although we are keeping the same station number. This is 3, 2 or 3 is almost same, we can say, although it is not shown in this figure. And then 3 to 4 is your combustion, where the fuel will be sprayed and mixed and then stabilized with the help of flame holders, which are basically gutters is being used as a flame stabilizer, and expanded in nozzle, that is 4 to 9, right? So why we don't need a compression here? Because of fact that the air will be entering at a very high speed. For example, if it is entering Mach number around 2.5, right, greater than equal to 2.5, right, or you can say it is equal to 2.5, and we'll have to now compress it or decelerated it, because we are compressing by decelerating the flow at the end of the air intake to 0.3. If you do a simple calculations of isentropic flow, you will find the pressure ratio of something around 17, 18 you can get. So then if I am getting a pressure ratio of 18 or 17, it is good enough. I need not to really go for a compressor, which is a very bulky and costly affair. So also the turbine I can help. But problem with this kind of thing is that it cannot start from the very beginning, right? Unless it achieves certain flight velocities, particularly supersonic kind of thing, the compression will be very, very low, right? Or it won't be zero. It will be zero at the static condition. So from the ground, it cannot be really, fly. So that is the limitation of this. So if you look at, there is another important aspect, that you can have, add more amount of fuel such that it can go to the temperature of 2000 Kelvin, because there is no rotary elements in it. So there is no material problem, although material problem about the combustor liner will be there, but that is being stationary, so you can manage to cool it, design properly, because with the nowadays good exotic materials have come up, you can go a little more beyond the 2000 Kelvin. But earlier days it was people are restricting to 1400, 1500 Kelvin kind of thing, even in the ramjet, because of. But when the designer, they have used their mind and come up with ideas how to, develop, how to operate the ramjet engine with the even existing materials. So that is the innovativeness of the design. So therefore, we always work with constraint, and whenever we work with constraint, we get a lot of ideas. So whenever you face problem, you will have to see that I will have to do something, so that I will use my mind, so that I will get the problem to be solved, right? So that is very important, and it is the simplest of air breathing engine, because it is devoid of gas turbines and rotating elements like turbines and compressors. Of course, as I told, the pressure ratio is limited by the flight Mach number and performance of air intake, that we will see as you go along. It cannot develop the static thrust itself. But question is, if it cannot develop, right, I cannot really use this unless otherwise I am having another aid to do that. For example, I can take, carry a missile of, based on the ramjet principle with a rocket, or in an aircraft, supersonic aircraft, fighter aircraft, then I launch. But if I want to, no, I am not happy with that, I want to use a ramjet from the ground itself, what I have to do? What are the ideas? Can anybody tell me?
Pulse jet.
Huh?
Pulse jet.
Pulse jet itself I can use. Why should I use ramjet? Right?
Rocket.
Rocket is already being used. So also aircraft. But I want to do something. So what I have to do? Huh? So what I am thinking, I will leave this question to you, right? And think about it. If you come up some ideas without looking at existing one, then it will be interesting to discuss. Okay. Otherwise, some ideas I can give. I don't want to give at this moment. Later on, we'll see. So let us look at what are the processes that involve. As you told that 0 to 2 is basically the compression. In a TS diagram, I can write down 0 to 2, that is the compression, right? Isentropic process, isentropic compression. But if I look at in a PV diagram, how it will be? Compression process 0 to 2, T2, it will be T2, right? And then TT2 from this station to what you call 4, it is the compression, that is constant pressure combustion, right? This is compression, right? So if I look at in PV diagram, it will be very simple. That is a constant pressure. Pressure is not remaining constant. And PT4 to P9, it will be expansion. Expansion where? Expansion in a nozzle. That is isentropic expansion. So it will be TT4, and this station is basically 9. So, and I am just saying it is basically 4 station, you can say, because total, we are talking about totally. Keep in mind, whenever I am talking about ratio in combustion chamber, what I will be saying, it will be pi B will be PT4 by PT2, right? Total I am considering. If I say it is tau B, it will be similar, TT4 by TT2, right? But whereas when I am coming over here, it is the static condition at the exit of the nozzle. At the inlet, it is also static condition. Keep this in mind, very important point, right? So we will be using those things and see that whether we can use how we can use this thing for our analysis. Is that clear? Any doubt in this? Because it's a very important thing, and we will be using similar stuff, processes describing in the process diagram like TS, PV, I can have HS, I can have some other thing as well, right? I can have TV, right? So you should think about this, how I can, describe the processes in various ways, because that will help you to enrich your mind. So the thrust equation for ramjet engine is basically thrust is equal to m dot 9 V9 minus m dot naught V0 plus A9 P9 minus P0. And keep in mind that what we are assuming in ideal cycle, it is an fully expanded nozzle. So therefore P9 is equal to P0. So therefore it is thrust is equal to m0 V9 minus m0 V0 only, contributed from the momentum. What we are trying to do? We are trying to now express these equations in terms of various ratios, so that we can vary and see what we are doing. That is, you should keep in mind, it is involves a lot of algebra. So, and as I told, it is P9 P0, and then m0 9 is equal to m0, right? That we are assuming. That means whatever the mass is exiting, it is whatever the equal to mass is entering. That means we are neglecting the mass of fuel being added, which is not a right thing, but we are doing for simplicity, right? What I am saying, maybe I can write down here, m0 9 is equal to m0 naught plus m dot f. This we are saying it is small as compared to m0. That's why it is neglected, right? So is equal to m0, approximately not true. So what I'll do, I can write down this expression. I'll take this m0 9 and a0. Then I am getting v9 by a0, right? What I'll do, I'll basically find out this a0, right? A0 here. So this is nothing but your m0, right? And what we'll do, if you look at a0 is the speed of sound, right? Isn't it? This is the speed of sound. Sound where?
Ambient.
Ambient or the free stream, right? Free stream speed. And m0 is the free stream Mach number. Free stream Mach number. And this a0 is nothing but root over gamma r t0, right? And you can in some place you can see this is gamma naught basically corresponding to the your this, which you will be using not in ideal cycle but in the real cycle. So I can write down v9 by a0 whole square is equal to, by definition, a9 square m9 square divided by a0 square, and this a9 square is nothing but gamma 9 r9 t9, and we are assuming this gamma 9 equal to the gamma naught, and r9 is same as that r0. So what we will be getting is, right, is basically t9 by t0 m9 square. That is, right. So if you look at, I am getting here v9 by a0 whole square is equal to t9 by t0 m9 square. I will be writing the same thing in the next slide. So is that clear? So, and equation 3 becomes v9 by a0 whole square equals t9 by t0 m9 square. So if you look at m9 square, I can express for isentropic process, right, for the, because the expansion is taking place in the nozzle. Can I not write down what will be the m9 in terms of pressure ratio? Just using isentropic relationship, right? So I can write down that m9 square is nothing but 2 divided by gamma minus 1 pt9 by p9 power to the gamma minus 1 divided by gamma minus 1. This is from the isentropic relationship for the pt9 by p9, right? Nothing, I've just rewritten, right? So what we will do now, we will have to basically look at this pt9 by p9, how it is, how we can express in terms of various pressure ratios. So pt9 by 9 can be expressed in terms of pressure ratio across each component. What I'll do, I can write down pt9 by p9 is equal to pt9 by pt4 into pt4 by pt2 into pt2 by pt0 into pt by p0 into p0 by p9. And this is equal to 1. Why? Because p9 is equal to p0. Fully expanded what we have done. So if you look at what is this one, this is nothing but your pi n, the pressure ratio in the nozzle, total pressure ratio in the nozzle, and this is nothing but your pi v, pt4 by 2, this is the combustors, right? And this is nothing but your pi d, and this is nothing but your pi r. Keep in mind that this is pt not by p0. That means total, right, to the static. That's why it's saying it is pi r. By definition, of course, because I have defined that thing, next to it. Okay. So now what we will do now, we are saying this pressure, that means the Mach number, exit Mach number will be dependent on these pressure ratios. You are getting 1, but now it is, too many. Right? Yes or no? And the same thing we will be doing for turbojet, turbofan, turboprop also. Right? Because we are now looking at each component, how they will be affecting the exit velocity. As exit velocity will be affecting the thrust, right? For a particular, of course, the flight magnitude. So let us, and if you look at what is this pi n by your assumption, pi n will be 1 or not? Total pressure ratio across the nozzle is 1 because there is no loss. So pi n will be 1. And what about this pi b? That is also 1. Burner. Pi d, isentropic compression. So therefore it will be 1. Can I say pi r is equal to 1? Can I say? I cannot, because Mach number, it is not total, it is basically, except all these things, pressure ratio, this was the pressure ratio which is with respect to static. So this is nothing but your, what you call, 1 minus gamma minus 1 divided by 2 Pt by P9, right? No, sorry, M9 square, right? That one. So
why across burner the pressure?
That is the assumption we have made. You look at your assumptions. We have looked at the total pressure ratio across the combustor will be 0. Total pressure loss. If total pressure loss is 0, then PT9 divided by PT2 will be 1. No pressure losses. Right. But however, in real situation it won't. Ideal situation it is yes. So what we will do, we are getting pi n, pi b, pi d is equal to 1. So Pt9 by P9 is equal to pi r. Right. And now expression of M9 can be expressed as, M9 is equal to 2 divided by gamma minus 1, Pt9 by P9, gamma minus 1, gamma minus 1. So what will say, this is nothing but your pi r. If you look at pi r power to the gamma minus 1 is nothing but your tau r. Yes or no? Because I can relate this isentropic temperature ratio to pressure ratio. Isentropic pressure ratio, right? We know those expressions. So therefore, but whereas the pi r gamma tau r is nothing but 1 plus gamma minus 1 divided by 2 m naught square. If I will substitute over here, what I will get? I will get gamma minus 1 to m naught square minus 1. So this will cancel it out, right? And multiplied by 2 gamma minus 1, right? So what I will get? I will get this also will be cancelling out. So 2 to cancel it out is equal to m naught square. What is saying? Is saying it's a very interesting statement. Is saying the exit Mach number for an ideal ramjet engine is equal to the flight Mach number. That means what really is happening? That means whatever the velocity of air which will be entering into the ramjet will be same as the exit velocity of the engine? Certainly no. It is the Mach number which is same. Under ideal condition, real situation it won't be. Right? So that is the interesting part how is here, but you should not assume that nozzle exit velocity V9 is equal to the V0 or the flight velocity. Certainly no. Okay. So now we look at how we can look at this T9 by T0, and so T9 by T0 temperature ratio I can write down as TT9 divided by T0 divided by TT9 by T0. Can I not write like this? Absolutely no problem, because it's just you rewriting that. Now we will be looking at how we can say this TT9 by T0, and keep in mind this TT9 by T9 be related to what? Pressure ratio, temperature ratio, all those things can be related, right? And we will now look at T9 by T0 in terms of temperature ratio. I can write down TT9 by T0 is equal to TT9 divided by TT4 into TT4 by TT2 into TT2 by TT0 Tt naught by T naught, right? So if you look at this is temperature ratio, what is happening, right? This is nothing but your, this portion is nothing but your tau n, this is nothing but your tau b, this is nothing but your Tt2 by T naught tau r, tau d, and this is of course the tau r, right? But if I look at this, can I say that tau n is equal to 1 total, because we are not adding any heat, nor you are taking any heat out of it. Adiabatic condition, isentropic expansion, right? So therefore I can say this is 1. Can I say that tau b is equal to 1? Right, no? Can I say?
No.
I cannot, I am adding heat, right? So therefore the total temperature ratio across the burner or the combustor cannot be 1. What about tau d? I can say it is
Constant.
1, not constant, 1. Ratio is 1, right? And so therefore and tau r, can I say it is equal to 1? Certainly no, right? Because it is the flight dependent on the flight Mach number, right? Okay, it can never be 1, it will be more than 1 always, unless otherwise flight Mach number is 0, there it will be 1, right? So therefore I can say that T9 by T naught is nothing but tau b dot tau. That means multiplication basically. In this case I have used. So T9 by T naught is nothing but Tt9 divided by T naught, right? And Tt9 by T9, if you look at that, is equal to tau r. We have already seen that earlier. So it will cancel it out, you will get tau b. That means T9 by T naught is nothing but tau b. And of course this I have already told you earlier that how it is Tt9 by T9 is nothing but your pi r gamma minus 1, there is nothing but your tau, right? We have already derived this thing, so we need not to repeat it. So now we will have to look at the combustors, and keep in mind that we are assuming this combustion chamber the flow to be one dimensional, but in real situation it cannot never be, okay? And we are assuming that certain amount of air is entering and fuel being added, and it is going out with certain mass flow rate of air and fuel. So we can carry considering the flow to be one dimensional and steady flow, that always we are assuming in this analysis, which I think I didn't mention, that is a steady flow, okay? And even in real cycle we will be assuming the flow to be steady, that you keep in mind. So therefore it will be m dot 2 STT3 minus m dot f delta SC is equal to m dot 4 ST4. And what we are assuming here, that continuity equation, that m dot 4 is equal to m dot f plus into m dot 3, and we are saying m dot f in this equation particularly less than m dot very very small. So therefore we are saying that is m dot 4 is equal to m dot 3 is equal to m dot air, how much air is entering. And we are assuming calorific perfect gas, so therefore Cp3 is equal to Cp4 and Cp, right? So if I look at this, if I can write down this expression, I can write down m dot, equation 9 I am writing, Cp T3 plus m dot f delta Sc, that is the heat of combustion, m dot A and Cp Tt4, right? If I could write this expression further, simplify, what I will get? I will get m dot f delta Sc is nothing but m dot A Cp T Tt2, because T3 is equal to Tt2, right? So in this place I can write down Tt2. So I can take this out, m dot A Cp Tt2 and Tt4 divided by T2 minus 1. So what I can write down here basically, m dot f delta Sc is equal to m dot a Cp, right, and Tt2 minus Tt4, and from that I can get this, like if I take Tt4 out, sorry, there is some problem, okay, Tt4 minus Tt2, okay, so if we take this out, you will get Tt4 by Tt2. So let us define f is equal to m dot f by a, and then from that expression I will get m dot f divided by m dot a is equal to Cp Tt2 divided by delta Sc is Tt4 divided by Tt2, and this is nothing but your tau b by definition, right, because we are assuming Tt2 is equal to Tt3. There is no compressor here, so therefore we are using. And keep in mind that this Tt2 will be same as Tt0, right, because the Tt0 is equal to Tt2 and no heat being added as shown in the what we call TS diagram. So therefore I can write down Tt0 is equal to Tt0 divided by T0, and this by definition is nothing but tau r, so T0 by tau r. Then we can write down as f is equal to m dot f by m dot a is equal to Cp T0 tau r delta Sc tau b minus 1. So now we shall write down basically the one definition which we will be using. I didn't define, let me define that. Is a tau lambda. This is a total enthalpy at the burner exit. That is, you can say it is a there is a little mistake here. So 4 and T4, and this is not required. So Tt4 by Tt2 and T2 by this. So will be tau b into tau r. Right. The total enthalpy at the burner exit, right, will be Cp4 Tt4 divided by this thing Cp0 by T0. So that I can say that Cp this will cancel it out. So therefore Tt4 by Tt2 is equal to Tt2 by T0 equal to tau b by tau r. That means what you are saying, tau lambda is basically tau b tau r, right? And this will be using some places. So coming to that, like I can write down this f is equal to m dot f Cp T0 delta Sc tau b tau r. I can write down tau lambda, right, and minus tau r. So V9 by A naught square, if you look at what we have done, we have find out T9 by T0 M9 square, and this is nothing but your tau b, and M9 is nothing but your M0 square, so that became tau b M0 whole square. So then our expression for the thrust, if you look at, it will be in this place, what we'll be using is basically root over tau b M0. So if I take this M0 out, it will be M0 A0 square M0 root over tau b minus 1. This is a very, very simple expression. What it says to you, it says that thrust will be dependent on the amount of mass flow rate entering into the engine. It will be dependent on also the flight Mach number, and it will be also dependent on tau b. That means how much energy you are being added. Tau b will be representing temperature ratio across the burner, which will be dictated by how much fuel you are being burned, so that total temperature will increase, right? So this is the simple expression we are getting, and we will be varying these parameters and see how it is dependent on what and what are the conclusions. So that's why you call it as a parametric segment. Rewriting equation to get a specific thrust, because if I just divide it by m dot a here, m dot a, okay, m dot a or m naught. So then I will get specific thrust a naught into V9 by a naught minus m naught. So that you can write down a naught m naught root over tau v minus v. Basically the same thing, only this is the specific thrust, right? And that is the thrust. So now what we will do, we will look at TSFC, just put these values f and then specific thrust you will get. There are several terms are coming into pictures, and of course it is a function of similar stuff except the delta SC has come into pictures, right? And propulsive efficiency will be, you can express in terms of tau v, right? In place of tau v, you can talk about tau lambda by tau r, because tau v is related to tau lambda, or tau lambda is related to tau v and tau r. We know that tau lambda is equal to tau v, tau r. And if you look at thermal efficiency, it will be similar. You can note that the thermal efficiency is equal to 1 minus tau r. That means it is dependent on only on the flight Mach number. It is not dependent on tau v and other things. Like how much heat being added is not really this thing. That is a very interesting result, right? And overall efficiency, of course, is a multiplication of that, which is dependent both on the tau r and tau v, because tau lambda, when I am saying this expression, it is basically tau v, right? Because tau lambda is tau v by tau r, tau lambda is equal to tau v by tau r, so it will be, coming into pictures. So, what I say, we are armed with all these, expressions, right? What we'll have to do, we'll have to vary these parameters, and which will be governed by altitude, right? It will be governed by flight Mach number, it will be governed by the temperature, at the exit of the components, right? So we will be doing that maybe in the next class, right? Because you may be having class after this, okay? Fine.